Okay, so today you're going to be getting your in-class notes through this video. So anything that is on the screen that's not in your note packet, those are your notes that you're supposed to get. Sorry, I have a little bit of a scratchy nose. So forces. Yesterday during the broom ball activity, we talked about how push and pull on objects, more specifically push for the broom ball activity, but how pushing an object can change its speed, can change its direction, and some other effects of trying to move objects that have a lot of mass, objects that don't have a lot of mass, and all of that leads us to our discussion on forces and how they affect motion. So we have observed that in order to move an object, we must apply a push or a pull. We can call that push or pull on an object a force. That is the definition of force, any push or pull on an object. Now, in nature, there are four fundamental forces: gravity, electromagnetic force, strong and weak nuclear forces. The electromagnetic force is the force of attraction or repulsion between electric and magnetic fields. So when magnets attract each other, or a magnet attracts something that is magnetic, that's part of the electromagnetic force. If you have electrically charged particles and there's an attraction, like when you get shocked touching a piece of metal, or just any electric field interaction, that's part of the electromagnetic force as well. And then we also had the strong nuclear and weak nuclear forces. The strong nuclear force, which is the strongest of the four natural forces, is what causes protons and neutrons in the nucleus to stick to each other. We talked about that earlier this year when we talked about the atom. We have these subatomic particles, the protons and neutrons, that are in the nucleus, and something has to be holding them together, and that something is the strong nuclear force. And then there's also the weak nuclear force, which is involved in some complicated stuff that we're not going to spend time talking about. The fourth, and the one that we have the most experience with, is gravity, or gravitational forces are defined as a force that is exerted between any two objects that have mass and are separated by some distance. Okay, this is actually Newton's law. If I get my pen to work here. Okay. Newton's law of gravity. So Isaac Newton also defined this. So any two objects that have mass and are separated by a distance do exert an attractive force on each other, and that's the force of gravity. And mass plays a huge role in this effect. So as an example, two people sitting near each other do exert a gravitational force on each other. So you and the person sitting next to you, you have mass, you're separated by some distance, you do exert gravity on one another. But your masses are not very big. And so that gravitational pull between the two of you is very, very weak, especially when you compare it to the gravitational pull between you and the Earth, because the Earth has tons and tons of mass. And so there the effect is much larger, and so that's why you fall off of things and you get pulled down towards the ground. So in order for an object to move, there does have to be sufficient force to actually cause a movement to occur. And the little bit of gravitational pull between you and the person next to you or other objects is not strong enough to make that happen. Gravity is also known as a long-range force. Long-range forces, or field forces, are ones that are exerted between two objects that are not in physical contact. So you don't have to be standing on the ground for gravity to be pulling on you. Okay, if you jump off of something, gravity will pull you to the ground, even though you're not in contact with the Earth. So that's a long-range force. Just like magnets, if you get a magnet close enough to a piece of metal, it will lift or push that object. Okay, it doesn't have to be in physical contact. When forces are exerted between two things, such as between the broom and the ball in our broom ball activity, anytime those forces only occur when things are in contact, those forces are called contact forces. Some examples of contact forces: friction. Friction that opposes the motion of an object. There are three kinds: static, sliding, and rolling friction. Static friction is a force of friction that keeps things from moving. So if you ever, as a kid, went down a slide at a playground and got stuck and you were on that incline and weren't moving, static friction was holding you in place, keeping you from going down the slide. When you were sliding down the slide, that's when you experience sliding friction. If you play baseball or softball, you experience this too, sliding into a base. Rolling friction is what you get anytime an object rolls across the surface. So for instance, tires on a car. Normal force. Anytime an object sits on the surface of something, so your Chromebook on top of your desk, gravity is pulling that Chromebook down and it's pressing down on the surface of your desk. Well, the desk itself also pushes back up on it. So normal force is a force exerted up and perpendicular to any surface that is caused when an object pushes down on that surface. So if you take your hand and you start pushing down on the top of your desk, the harder you push down, the greater that normal force is going back up against your hand. Tension force. Tension force is caused when a cable or springs are pushing on an object. So if you tie a rope to something and pull, you're not actually pulling on the object itself. You're pulling on the rope or the chain or whatever it might be, and then that is attached to the object that you're pulling. And so we call that tension force because there's tension within that cable, or if it's a spring, tension within that spring. So that's tension force. Now, as far as whether or not an object moves when a force is put on it, we have to look at, are the forces on the object balanced or unbalanced? So when we push and pull on things, they move, right? Well, no. I'm sure there's been times where you've tried to lift something or push something or pull something and it just didn't want to go anywhere. So for instance, tug of war. We got two people each pulling in opposite directions, and if they each pull at the same amount of force, does the rope move? And the answer to that is no. Okay, if you've ever seen a tug of war with two evenly matched teams, nothing really happens because you're both pulling in each opposite direction. One going this way, one going that way. Same amount of force, nothing moves. But if you've ever seen a tug of war between two teams where one team was way stronger than the other, so for instance in our second example here, the person to the right pulls with a lot more force compared to the other side, well then what's going to happen? Well, everything moves to the right. Okay? Because in one example, the two forces in our top example up here, everything is being pulled opposite directions, equal amounts of force, so they balance each other out. Okay? Whereas in the second example, we have such a much larger force in one direction, then it's greater, it's stronger, it's pulling with more force than the small force, and everything starts to slide in that direction. So in one example, the forces are balanced, and in the other example, the forces are unbalanced. By definition, for the first example, balanced forces, when the forces on an object balance each other, they result in zero net force. Okay, net force means the total or sum of all forces. In the second example, we have unbalanced forces, and this is when forces on an object do not balance each other out, resulting in a net force moving the object in one direction or the other. So, here we go. So as far as how do those forces acting on the object, whether they're balanced or unbalanced, cause a change in motion? Well, this is now we're going to start talking about Newton's laws of motion. We talked about how Newton was investigating motion, the movement of objects. He was collecting position, time data, analyzed it, learned about velocity, analyzed the velocity, time information, came up with the concept of acceleration. Well, in doing all these investigations, when he finished, he came up with 3 laws of motion to describe how objects behave when they have forces acting on them. So this was the results of all of the stuff that he did previously. So in the early days of physics, there were a lot of misconceptions about the relationship between motion and forces, and we've talked about some of that. Some of it has come up in class, and this was really what he was trying to figure out in the later part of the 17th century. In Newton's attempt to identify the proper motion relationships, he discovered he needed new math. We talked about that too, where he developed calculus, derivatives, integrals, learning how to measure position over time, velocity over time, acceleration over time, and all those things. Newton's first law of motion. So with friction again is the force that opposes motion. If you were to slide a book along the ground, it would eventually stop because of friction. Okay. If we were to slide this book on ice, it would travel a lot farther. Well, why? Well, on ice, it would have much less friction. And as that book slides, the only force that is really affecting its motion is that force of friction as it slides back and forth. And if we do a little diagram for it, and here's the book. It's going like this, so it's moving, its velocity, it's in that direction, and we'd have friction opposing that. Okay. And that's the only force acting on it as it slides left to right. The only force in the left to right horizontal. Okay. So if we have a big frictional force, it's going to stop real fast. If we have a small frictional force, it's going to take a lot longer for it to come to a stop. Now, if we could reduce all friction to zero, so absolutely zero friction, no friction whatsoever, the question is how far would the book travel? Well, if it's moving and there's no force to oppose the motion, it wouldn't stop. It's never going to stop because there's nothing to cause its motion to change. So Newton defined his first law of motion as any object at rest, which means not moving, will stay at rest, or an object in motion at a constant velocity will stay in motion unless acted upon by an unbalanced force. So when the book slides across the ground and experiences friction, the friction is unbalanced. There's nothing to balance it out, and so the book slides to a stop. Its motion changes. It goes from moving to rest. When we played the broom ball activity, the bowling ball was at rest, and then we applied an unbalanced force, the push of the broom on the bowling ball, and got it to start moving. Okay. Now, when I say at a constant velocity, it's important to note the use of the term velocity because if the speed remains unchanged, if the object changes direction, it changes its velocity. And velocity is not just speed, but also direction. So when we were turning the bowling ball around the bucket during the broom ball activity, it might not have looked like its speed was changing, but because its direction was changing, then it also is experiencing unbalanced forces because we're changing its motion. So you can speed it up, you can slow it down, you can change its direction. Okay. So this also requires an unbalanced force. Anytime something speeds up or slows down or changes direction, we have an unbalanced force acting on it. That also means that if the forces are balanced, like in our first tug of war example, the two forces pulling to left and right, same amount of force, nothing moves. Everything stays at rest. But that also means that if we have an object that is moving and it's experiencing balanced forces, it will just keep on moving forever. No change in its motion until it experiences that unbalanced force. Think about a baseball being thrown through outer space. Okay, there's no air resistance. It's not going to interact with gravity pulling it down. There's no friction. There's nothing acting on it. So once that baseball starts moving, all the forces on it are completely balanced. There's no net force on it, so it would just keep moving forever through space. So if we analyze both situations, first for an object at rest, what forces are acting on it? Well, we would have gravity pulling it down, and we would have the normal force pulling it up, and those two forces are equal to each other, and so it just sits there at rest. If it's sitting on the ground at rest and there's nothing pushing it to the left or right, then all the forces on the block are balanced. So it's at rest. It does have forces acting on it, but gravity is being balanced by the normal force that's pushing back up on the block as the block pushes down on the ground, and it doesn't move. No change in motion. Newton's first law. Only unbalanced forces can change the motion of an object. Okay. But what if we put an unbalanced force on the block? So same block, we got gravity, we've got the normal force pushing back up on it, but now we're going to push on the block to the right. Because of that, the block will slide to the right. Because of the unbalanced force. So just like in the broom ball activity, broom ball activity, the ball accelerates in the direction of the push. So when we were pushing it towards that first corner, that's the direction that the ball accelerates. That's the direction that it was speeding up in. We talked about that yesterday during our analysis of it. So we have this force that is unbalanced in the problem, and so the motion of the object is going to change. Now, as far as an object in motion, if an object is sliding on the ground at constant velocity, what forces are acting on it? Well, we always have gravity, and as long as it's sitting on the surface, it has that normal force. And if it's sliding along, we could, at a constant velocity, we could also assume that there's no friction here. And we put little whooshies in there, so it's moving along. So even if it's in motion, if there are no forces acting to the left or right, then the object's motion will not change. The hover puck is a great example of this. It slides along the ground almost completely without friction. And so if we had good batteries in it and had a nice little cloud of air that it could float on, we could push it, and it would just keep on going down the hallway at a constant speed until it eventually bumps into something. Okay. But what if we push against the object that is moving? So we've got gravity again. We've got our normal. And we've got our whooshies because it's still moving to the right, and we're going to push against it now. Well, we saw this too in the broom ball activity. The ball's rolling towards that corner. You want it to turn the corner, so you start pushing against the object, and the object begins to slow down. So it would slow to a stop. The velocity is positive, but the force is in the opposite direction, which causes the block to stop. Okay, negative acceleration. Only negative due to the direction. The net force and the acceleration on the object always have the same sign. We saw this yesterday. Kind of just went by it, thought it was interesting, but that's the reason why the acceleration gets the sign that it does. Okay, when an object speeds up, if it's going in the positive direction, the acceleration is positive because that's the direction that there's a force pushing it in. If it's slowing it down, it's pushing in the opposite direction, so the signs are opposite. Or if it was speeding up in the negative direction, that means that the force was pushing it in the negative direction. If you push against it to slow it down, then the force is pushing in the positive direction, and so the signs flip. That's the reason why. Positive acceleration does not mean speeding up. Sometimes it does, sometimes it doesn't. Negative acceleration does not mean slowing down. Sometimes it does, sometimes it doesn't. It's all about the direction of force. Force changes the motion of objects. If we change the motion of an object, it has to speed up, slow down, or change direction. That is acceleration. Another idea that came up out of our activity yesterday was the idea of the object's mass having a factor in this. And the object's mass is related to the idea of inertia. Inertia is dependent upon an object's mass, not velocity. We talked about yesterday, we saw it in class, how you can stop the bowling ball with a tiny amount of force, okay, whether it's going fast or slow. Okay. The object's mass, not the speed, has an effect on its motion. So, if we consider the situation here, we've got a tennis ball and we've got a giant rock. It's actually the Rock of Gibraltar, which is why it says 1620 on it. But if we take these two objects and toss them at somebody and they're going to get bonked with it, well, which one is going to be easier to stop? The tennis ball. Tennis ball might hit you in the head. It might not feel very good, but you're going to be able to stop the tennis ball. You get this giant boulder thrown at you, you're not going to be able to stop the boulder. Okay, it'd be no different than if we took the 16-pound bowling ball and threw it at somebody. You're probably not going to be able to catch it and not be moved by it somehow. Okay, so because the rock has more mass, we say it has more inertia, and what that means is that it will resist changing its motion. Okay, inertia is all about the object's willingness to change its motion. Okay, more mass means more inertia, which means harder to change its motion. The object will resist changing its motion because it has more mass. So speed doesn't have anything to do with it. I mean, think about it. You could have a marshmallow coming at you at 100 miles an hour. That's going to be easier to stop than somebody lobbing the bowling ball at you at 2 miles an hour. Okay, it's going to resist changing its motion more because it has more mass. Okay, that's it. We're done. You do have an assignment for tomorrow. It's posted to Edmodo, so make sure you pull that up, answer all the questions, complete sentences in your notebook, and we'll be talking about it at the start of the hour tomorrow.